Another thing which is very important that we are going to say is about the operating characteristics of the queuing system. So you should be making no, you should be uh, keeping in mind the difference between the elements of queuing system and the operating characteristics. There shouldn't be any confusion between these two things. These two things are totally different, and that difference you should particularly remember. So now the first operating characteristics of a queuing system is, firstly we are going to start with the queue length, and it is denoted by LQ, right? A capital L and a small q. So what is it? What is the queue length? It is the average number of the customers in the queue waiting to get served. This excludes the customers being served. So very easy. We have also seen it no, previously, but now we have just named the terminology because we are going to use it as in use it in the numericals, right? So the average number of the customers in the queue waiting to get served is called as the queuing length, and you will have to remember it do not no, it excludes the customers that are being served, right? Nextly we have a system length. Now system length is specifically what it is denoted by a capital L and a small s, right? So L for length and S for system. Similarly here it was L for length and Q for Q. Right now, what is the meaning of the system length? It is the average number of the customers in the system, includes those waiting and getting served, right? So what is a system? Entire, but all the people in all the customers who are waiting in a queue plus those which are getting served are the part of the system. Hence the system length will be what it includes those those waiting in the queue and also getting the served, and it is denoted by a terminology called as LS, right? So now what next very important operating characteristics is the waiting time in a queue, that is denoted by capital W and small q. It is the average time for which a customer has to wait in the queue to get the service, right? It is the average time for which the customer has to wait. Now the why average time, particularly time for every customer may be different. So here with the average time particularly will be uh, representing the characteristics of the waiting time in the queue, right? Similarly we have one more characteristics, and that is your WS, right? So it is the total time in the system. It is the average total time spent by a customer in the system from the moment he arrives till he is in the system. So that particularly will be including the waiting time and the service time. So this is very, very important. I hope that you have understood what is the queue and what is a system. Queue is only that particular line, or it is only only those particular customers who are waiting to get served. So those, that is called as the queue. And what is a system? System is that particular thing in which the customers are waiting for getting served, and also it also includes the customers being served. So this particularly is your system, right? Next is the utilization factor. It is denoted by rho, right? So it is the proportion of a time for the server actually spends with that particular customer. It is also it is also called as the traffic intensity. So it is the proportion of the time that a server actually spends with the customer. It is also denoted normally. It is also said as the traffic intensity. Let's move ahead and understand one few more terminologies. So now waiting time and idle cost. Now waiting time and idle cost are particularly why it is important to understand. Firstly, we have talked about this in the previous few lectures, but then too I wanted to show you it in a graphical format how the graph will be behaving for both waiting time and the idle time cost, right? So the waiting time cost that we no, waiting time cost, that is the what is included in the waiting time cost is the indirect loss of business, right? So the customer will not be entering into the queue that is very, very big, and he will be going elsewhere for his service. So what is that? That is the indirect loss of business. And now the waiting cost, no, it also, now this waiting time cost also includes the waiting cost of the equipment or the customer. So what will happen is that, for example, if the truck has come to get loaded or unloaded, so what will happen is that the truck driver and the truck is waiting to get unloaded or loaded. So what is that? There is the waiting cost of that customer or equipment that is happening, and this together can be termed as what? It together can be termed as your waiting time cost. Right now, what we are going, now what we have is the idle time cost. Now what is the idle time cost? It is the cost to the service facility which is remaining idle, right? So cost of idle service facility, even if there is no customer, the owner of the facility will have to pay its server, right? So all those servers which are particularly getting paid and they are not doing any work, so what will happen is that that is nothing but the cost of idle service facility, right? So in for the waiting time cost, if you see, there is too much demand for that particular facility, and in idle time cost, if you see, there is no demand for that service facility. Now what is a queuing problem, right? A queuing problem is like, now we'll have this particular are the problem, right? And what is the solution? Now solution, particularly I've also talked about the solution in few of the previous lectures. Now the solution is what? A solution is to schedule the flow of the units, right? So scheduling of the flow of the units, what will happen is that if there are more number of customers, so if we give the appointment to the customers, they will be coming according to their time and they don't have to wait. So that is called as the scheduling of that particular flow of units. And next is the providing proper number of facilities. Now here particularly why the facility would have been remaining idle, so it may so happen that there are like two or more stations which are serving that at that particular service facility. So at this particular juncture, if I have to reduce the idle time cost, so what I'll have to do is I'll have to reduce the station, right? So particularly these two is the solution. So what we are interested in, scheduling the flow of the units and providing proper number of the facilities at that particular location. Right now, if we graphically try to represent the waiting time cost, so what may happen is you will be getting this particular type of diagram, right, or this particular graph, right? So on your x-axis, I put down the increased service, and on the y-axis, you have the waiting time cost. So it is very obvious. See, if I'm having particularly less service, so if I do not have proper service, so what will happen? The waiting time cost will be more. Similarly, if I'm increasing my service, what will happen is that my waiting time cost will be less. So this is how the it is how the your waiting time cost will vary for the increased service, right? Now particularly let's understand how this cost of providing service will vary depending upon the increased service. Now what will happen if I'm increasing the service? The cost of providing that particular service will also what? It will also be also on the higher side. So same example, if we think of eating a vada pav at the street, so if you see, there is no quality of service that we get. And if there is no quality of the service that we get, particularly, or what we can say, I can't say it as there is no quality of service, it is minimal quality of the service what we get from a street side vendor who is selling the vada pav. So there is no, particularly the cost of providing service is very, very less. But that now particularly if I go to a five-star hotel and if I'm asking for a vada pav, what is there? They are particularly having the good service there. And what may happen is that particularly the cost of providing service will increase. Right now, what I can do is I particularly okay, just a second. Okay, now what I can do is I can draw a graph in which I am particularly for a particular increase for a particular service level, I can add the waiting time cost and I can also add the cost of providing service. So same thing is there. on y-axis I have on x-axis I have increased service, and on y-axis I am having now here the cost, right? Now what is happening here, I have represented, this is my waiting time cost, right? So this particular curve here, it is waiting time cost, and again particularly here is the this particular line which is moving in with having an angle of 45 degree and passing at passing near the origin is having particularly the cost of providing service. If I'm adding both of this cost and I'm representing it with a different curve, let's say that this particular curve, which is the total which is represented as the total expected cost. So it is what, it is just the addition of these two costs, that is the waiting time cost and the cost of providing service for a particular instance, for a particular increased service, right? So what may happen here is that I will be getting a I'll be getting a different curve here, which is including both of both my waiting cost as well as the uh, cost of providing service. So I'll be getting this particular curve, right? And now what is, now this particular curve is called as the total expected cost. And what I have to do is I have to reduce this total expected cost. Then only what will happen, my that particular service facility will be no, it will be in profit. Draw this particular line below. I'll be getting a point somewhere here. Let's say that that point is S. So what is here? The total expected cost is minimum at service level, denoted by S. So this is how this particularly can be represented on a graphical level. So now we are here for reducing the total expected cost for a service facility. Now, to begin with, we have seen the elements, various elements, right? Now that particularly there is a very interesting notation system that has been developed by the Kendall. So now we are going to see how this representation happens for the elements of queuing model, right? So the complete notation can be expressed as, right? So all this expression can be expressed as, in first bracket will include A/B/C bracket complete colon. Next bracket will include D/E/F and bracket close, right? So this particularly is called as the Kendall's notation. Now let's understand what is the meaning of A. Now here A is nothing but your arrival distribution, which is one of the element, right? We have already seen this Kendall in the elements. So A is nothing but it is arrival or inter-arrival distribution. B is what? B is your departure or service time distribution, right? Now C denotes the number of parallel service channels in the system, right? So I am sure that you are remembering now what is meant by service channel as well. Single service channel, multiple service channel, and in multiple service channel also we have seen if it is parallel or series, right? So here A denotes arrival distribution, B denotes here particularly it denotes the departure distribution, and C denotes here number of parallel service channel in the system, right? So this finishes our first bracket, which is A, B, C, right? Now next bracket is what? Next bracket is D, E, F. Now what is D? D is your service discipline. Now what are service discipline? We have already said first come first service, last come first service, zero, that is service in random order, right? Priority, pre-exemptive priority. So that is nothing but that is represented by this D. What is E? E is the maximum number of the customers allowed in the system. Even that particular thing we have seen as the part of the element of your queuing system. So what is E? It is E is the maximum number of the customers allowed in the system. We have F. F is nothing but your calling source or population. Even this was our part of your service discipline. So all these elements of the service discipline have been named as A, B, C, D, E, F. Now, what is represented by what symbol, that is important, right? So what is represented by A, what is represented by B, what is represented by C, that is very important when we are going to use this particular denotions, right? Now, in case of A, B, and D, so what was A? A was your A was your arrival distribution. B was particularly your departure distribution. So we are going to see particularly in when we have symbols A and B, what kind of particularly what kind of options do we have at this particular stage to replace this particular symbol. So if I have my arrival distribution, yesterday we have seen it can be a Poisson distribution or it can be an exponential distribution, but there are also some of the various kinds of distribution that the management researchers have drawn. So the Poisson distribution is also called as the Markovian distribution, and if your inter-arrival distribution is a Poisson distribution, it is to be represented by a symbol M. So at the place of A, what you are going to write it is M. Even if your service distribution is even if your service distribution is Poisson distribution, you'll be replacing this B symbol by writing the capital M, right? So this is your Poisson distribution, right? And now particularly even even for the exponential distribution, we are going to use the same symbol, that is M. So Poisson distribution and the exponential distribution, we do not have different symbol. You have to write it as the Markovian distribution only, right? So there are some other types of distribution also. It can be an Erlangian distribution, which is represented by EK, and if it is an Erlangian distribution, you will be replacing it by A, both your denotion symbols A and B by EK. There you also have a general independent arrival distribution, so your A will be getting replaced by GI there. You also have deterministic inter-arrival or service time, so the at that particular B point you'll be writing D. So for your A and B options, A and B symbols can be particularly it can be exchanged, or it can be represented by M, EK, GI, G, and D, depending upon what distribution is there. So these are the types of distribution that we normally have. At this particular time, do not get confused or stressed. We don't know about all these distributions, because for syllabus what we have, that I'm going to tell you. Now, what was your D? D was your service discipline. So for D, what you can put down is you can put down the symbols as FCFS, that is first come first serve. LCFS, it is last come first served. Zero, that is service in random order, and GD, that is your general discipline, right? So this particularly are the symbols that we are going to use for your D, right? So we are going to replace a D is by either of this, not by all of this. At a particular instant, it will be either FCFS or LCFS or SIRO or GD. Similarly, for A and B, it will be at a particular instant, it will be either M, it will be either EK, it will be either GI, G, or D, not all at the single time. So I'm hoping that you have understood what alterations that we are going to do for A and B symbol, and what alterations that we are going to do for the symbol D. Now this particular will vary. The symbols will be getting changed depending upon what have been given as a problem statement to us, right? Now for symbols E and F represent, what is E and F? It was a number of the what was E? It was the maximum number of the customers allowed in the system. And what was F? F is nothing but the population source, right? So we can for symbols E and F, either it will be a finite, if it is a finite number of customers and the finite population source, so we will be representing it by N, or it can be the infinite number of either it can be a finite or infinite. So if it is finite, we'll be representing it with the help of N, and if it is infinite, we'll be representing it with the symbol of infinity, right? So this particular is to be followed. Now for example, let's I've taken the example, right? So here it was A, B, C, D, E, F, right? So for A, I have written here M. For B, I have written it as EK, and for C, I have written it as 1. For D, I have written it as FCFS, right? Then for N, I have written for E, I have written it as N, and for F, I have written it as infinity, right? So what this particular suggests that now, with the help of this particular notation, what this particular suggests is that the Poisson arrival is there. Here M suggests that it is a Poisson arrival or a Markovian arrival. EK suggests that there is the Erlangian departure that is happening. One suggests that there is only a single server, that is, particularly it can, if it is a multi-server, you will be writing it as 2, 3, 4, 5, but one represent it is a single server. FCFS represent that there is a first come first serve discipline that has been followed, and suggest that there is the maximum allowable number of customers in that particular system is n, and what this particular suggests that you have an infinite source of population, right? So this is how this particular model is. This is how the Kendall notation will be helping us to write that particular model, right? So according to that particular thing, we have various types of model, right? So there can be a probabilistic model, there can be a deterministic model, and there can be a mixed queuing model, right? So in probabilistic model, these are the models that we normally have, right? So even now, particularly with this particular denotion, model 1 is called as Erlang model, and you can see the representation that it is having. It is m/m/1 and FCFS infinity, right? So this is how the model 1 is represented. This is how the model 2 is represented. This is how the model 3 is represented. Model 4, model 5, model 6, model 7, model 8, model 9, and model 10 cannot be represented by Kendall notation. It is called as the power supply model. Even you will be having the deterministic model, which is represented by this particular strategy, and you will be having the mixed queuing model, right? Now the good thing is that we do not have all these models for our study. We only have model number 1 for our study, which is the Erlang model, right? And what is the Erlang model? Erlang model is denoted by this particular thing, right? Now for all the numericals that in your examinations will be depending upon only the Erlang model. You have to take into consideration how the notation is being made. It is m/m/m. So what this particularly suggests is that there is a Poisson distribution for your arrival distribution is Poisson, your departure distribution is Poisson, and you have a single server at that particular location. What is denoted by FCFS is that the service discipline that will be followed is first come first serve service discipline. You have infinite number of customers, and also you have infinite your population sources also infinite, right? So this is how this model is being represented. So we have only this model 1 type for our syllabus, and that only we are going to think of, right?